Hi there, this is Ms. Page, and today we are going to be talking about how to find the inverse of a function in context. So if we have an equation or function that models a real situation, such as in this case we have an equation or function here that models the volume of a cube in terms of its side length s. So s times s times s, or s cubed. And so this one models the volume of a cube. That's our v. When we actually find the inverse function and represent the inverse, we are actually finding then a function that is s equals side equals, and that's what we have here. So the inverse models the measure of a cube's edge or side length relative to its volume. So we have s equals, and our independent variable here is v, so they switch. The mathematics is a little different, where the one thing we don't have to do is switch the variables, and we'll talk about that when we find the inverse. Another thing that we're going to be looking at is identifying the domain and range of the inverse in these context problems. So as we've learned before, the domain of an inverse is the range of the original function, and the range of the inverse was the domain of the original function. So in this case, using our volume of a cube situation, the original function is v of s. So s is our domain variable. So s is those edge measurements, and of course edge measurements have to be positive, so it says greater than 0. So that means that in our inverse function, s is now our range. So it's the edge measurements greater than 0. Here in the original function, v is our volume, so our volume measurements are the range, and so our volume measurements are greater than 0, because again, volume has to be a positive to make sense. And so here in the inverse it switches, and now v is our independent variable, so it becomes our domain. Volume measurements greater than 0. So we can actually use then our understanding of the original function's domain and range and just flip them, and we have the domain and range of the inverse in context. This information in your guided notes is just reminding you that in these polynomial structure functions that we undo things in the reverse order of operations, which we have talked about before. So let's go on to this example here. So in this example, we have the function d of t equals 16t squared, and it gives the distance d in feet. So that's our d variable, which is our dependent variable, like our y. So it's the distance d in feet that a dropped object falls. And that's in t seconds, and t is our independent variable, t. All right, so that means that t would represent domain values and d would represent range values. We'll then switch that, you will notice here in part B. But for part A, we want to write the inverse function, and this inverse function is to find the time in seconds. So since time is t, what this is telling us is we want a function that is t equals. So we are supposed to find a t equals function. And to do that then, what we'll have to do is take our d function and solve for t. So we have d of t equals our 16t squared. And when we had our generic functions like f of x equals and g of x equals, we changed those to a y. In a context function, something like d of t, you want to change to just your dependent variable here, which is d. So this we write as just d equals 16t squared. And now we're going to solve for t, undoing our algebra. So we'd undo our multiplication, dividing both sides by 16. So that gives us d divided by 16 would equal t squared. And then we'll take the square root of both sides. Again, like we talked about with these types of functions, we'll use the principal square root, the positive square root only. So we have the principal square root of d divided by 16 equals the principal square root of t squared. So our square and square root cancel, and this gives us t equals the square root of d divided by 16. The function notation, function form of this is t of d now. So we had d of t. This becomes t of d equals the square root of d divided by 16. And there's our inverse function. So over here in part B, we are looking at describing the domain and range of the inverse function model. And we are supposed to include restrictions, which means that if things have to be positive or non-negative or greater than 5, something like that, we include that information. All right, so here's probably the easiest way to do this, is to realize, okay, let's go back to the original description and identify in context what the domain and range would be. So the domain, again, is our independent variable, which is embedded in our function t. So t is the domain of our function. And that means that it's going to become the range of our inverse. So then the range, we want to do that one first, would be the time in seconds. And since time has to be what we call non-negative, it can't be negative, we include that restriction. So you can say where t is greater than or equal to 0, because we can't have 0 seconds. Or you could also say t is non-negative. Domain. So for domain of the inverse. So now that goes back to this. We have to realize our d is our dependent variable. So this is our range concept. So the distance in feet a dropped object falls, that is describing the range of the function. Therefore, it becomes the domain of the inverse. So the domain is the distance in feet. Always include units. Feet for distance, seconds for time. The distance in feet. A dropped object falls. Where, so we should realize that the distance it's falling would, and you can actually take your 0 and plug it in here. 16 times 0 squared is 0. So 0 feet is your smallest feet, can't fall in negative feet. So where d is non-negative, greater than or equal to 0. So you can say it that way, or again you can say d is non-negative. Like so. So there's our domain and range for our inverse descriptions. Part C, we're solving a problem involving one of our models here. So this says estimate how long it will take. So how long is a concept of time, not distance. How long something takes is a time concept, not a distance. So we want to use our t equals function, our t of d. So we use our t or t of d. I'm just going to write as t equals here since I'm doing a calculation. And specifically, we want to know the time it takes a penny dropped into a well to fall 48 feet. So the falling, remember, is our d value in feet. So we have the right units. So that means our t is going to be equal to the square root of 48 divided by 16. Now you might notice this is equal to 3. And then you can say this is just the square root of 3 and figure out what that is using your calculator. If you don't, make sure in your calculator that you have parentheses around this division for your radicand so that the calculator understands to divide first before taking the square root. So using our calculation, this to 3 decimal places is about 1.732. And t is our time in seconds, so that's our units. And we can then write our conclusion. So it will take a penny dropped into a well. About 1.732 seconds to fall 48 feet. Like so. All right, so we have a second example we're going to take a look at. So here we are dealing with, so we have this function m of L equals this decimal point 0.0000001 L cubed. We have a cubic function here. And it gives the mass m in kilograms of a red snapper, which is a fish, if you didn't know that. And picture over here of one. M is our mass, and so this is our dependent variable. And then it's dependent upon the length of the fish, the snapper, in centimeters. That's our L right there. So again, the first thing we're going to do is write the inverse function to find the length of a red snapper in centimeters, given its mass. So what that's telling us is that we want to take this function and we want to solve it for L. We want to find an L equals function. So I have my m of L equals 0.00001 L cubed. And so again, I want to take this function structure and just use my dependent variable of m. So m equals 0.00001 L cubed, and we're going to solve that for L. So again, we're going to undo this multiplication first, dividing both sides by this decimal. And that gives us equals L cubed. And then we're going to undo our power of 3 by taking the cube root of both sides. All right, and so over here, our cube and cube root undo each other and get our L equals. This over here, what we're looking at, is quite honestly not really the best form. This decimal here, we could do 1 divided by this decimal, and if it turns out to be a nice number, which it should be, because this is some power of 10 down here, it'd be much better if we write it as something times in rather than m divided by this. So take your calculators and do 1 divided by this decimal. And if you do this 1 divided by the decimal, what you get is 100,000. Much nicer than this m divided by this teeny tiny little decimal number. So we get L equals the cube root of 100,000 times m. And then function notation would do L of m. So we have L of m equals the cube root, I'm going to need some space over here, I guess, 100,000 m, like so. All right, this is a much more appropriate form for a function like this. When you can clean things up, you always do in mathematics. So now we're going to look at set part B, which is we want to describe the domain and range of that inverse function model, include those restrictions, so things that need to be positive or non-negative or greater than 7 or whatever it might be. All right, so again, I like to think it's easiest to use our function information. So we know our function here, m. So m is our dependent variable, so m is our range of this function. So the mass m in kilograms of a red snapper is the range of the function. Therefore, it becomes the domain of the inverse. So the domain of the inverse would be the mass in kilograms of a red snapper where our M value actually needs to be positive. 0 doesn't really make any sense in this case because a mass of 0 would mean actually the fish doesn't even exist. So really M just needs to be a positive number greater than 0. So you could say or M is positive. Your range. So your range had to be the domain of the original function. So the domain is our independent variable of L. So this is the domain of the function. And so it becomes the range of the inverse. So our length in centimeters is the domain, or is the range of our inverse. So our range of our inverse is the length in centimeters technically of the red snapper. So I'm going to go ahead and add that for details. And again, length has to be a positive number. 0 doesn't make any sense. 0 length, again, the fish doesn't exist. So where L is positive or L is greater than 0, whichever way you prefer. All right, and then part C, where we actually use our models. So here we are estimating the length of a red snapper. And so if we want to estimate the length, that's our L, so we want an L equals function, and that would be our inverse function here. So we're going to use L equals the cube root of 100,000 times M, and that then is, and our M value is our mass of 3.2 kilograms in the correct unit, so we're good there. So we are going to have our L equals the cube root of our 100,000 times 3.2. And for this we can use our calculator. So again, you could calculate this first and then take your cube root. If you want to do it all at once, make sure there's parentheses around that product. All right, if perhaps you haven't done a cube root on a calculator before, you have to make sure you use what's called really the nth root notation. Usually looks something like this on your calculator. And you have to indicate the index first, at least in the classroom calculators, that's how it works. So if you're using one of the classroom type calculators, you would type in your 3, and then you'd pull up your x root, and then you used to open a parenthesis and do your 100,000 times your 3.2, close your parenthesis and hit equals. And what you should get to 3 decimal places again is the number 68.399. And this would be our length, and length, if you recall, is measured in centimeters. So this is in centimeters, and then we can write our conclusion. So, given a mass of 3.2 kilograms, the red snapper is about 68.399 centimeters in length, or long. Like so. All right, so there's a couple of examples. One each of what involves, an inverse that's a square root and an inverse that's a cube root. A little information about calculations with calculators, domain and range. So you can go ahead now and begin your assignment. Have a good day.